Have you ever sat down and thought about subatomic particles interacting in the universe? No? Well, that's okay, because I'm here to talk about bonds. Ionic bonds. This is the periodic table. I know looking at it at first can be a bit scary, but understanding the periodic table is fundamental to understanding ionic bonds. The periodic table is organized in rows and columns. Rows are called periods, and columns are called groups. In the next clip, you can see me coloring in the periodic table to help visualize the different types of elements that are present. Metals are colored in purple, and they tend to be on the left side of the periodic table. Non-metals are on the right. In between, we have metalloids, which share the properties of both. Another way that you can identify atoms is by their unique electron configuration structure. Noble gases are the popular girls of the periodic table. Everyone either wants to be them or look like them.
Neutral atoms are atoms that have a charge that equals 0, meaning their negative values and their positive values equal 0. So for instance, beryllium has 4 protons, so that means to balance out 4 protons or 4 positives, you need 4 minuses, meaning that beryllium as a neutral atom has 4 electrons. Now just because we can tell you how many electrons are present in a neutral atom doesn't mean that we can explain how it can be written into simpler forms, like using the electron configuration method. In this example, we are using beryllium again to show how many electrons it has using suborbitals, which are represented by different colors. Beryllium has 4 electrons, which means that it takes up 2 squares. So we have the 1s square, and then we have the 2s square, both of which are filled up by electrons. But this can get long and lengthy, so there is a shortened version of this called core electron configuration, where you write out the closest noble gas and then add on whatever electrons are left over after you write it out. So this example would be helium 2s2, because it is a helium atom at its core plus 2 valence electrons.
Metals, metalloids, and nonmetals tend to share the same properties amongst their groups. Metals tend to not want their electrons, while nonmetals tend to want more electrons. In this example, I am writing out the electron configuration for sodium. And then I'm using core configuration to show the nearest noble gas to sodium. Now sodium wants to look like neon, which is 1 electron behind it. So in order to do that, sodium is going to lose an electron. A general rule of thumb to go by is that metals are always going to move backwards to look like a noble gas, while nonmetals are always going to move forwards. This is an example of a nonmetal moving forwards to look like a noble gas. So fluorine by itself is a neutral atom, and it wants to gain a negative particle, an electron, to look like neon. So the number of electrons is greater than the number of protons, meaning that it is a negatively charged ion now. Elements love to mingle and form compounds. That's where ions come into play. Some elements lose electrons and become positively charged, called cations, while others gain electrons and become negatively charged, called anions. Let's look at some examples.
This is a dot diagram, which is used to show the number of valence electrons an atom has. So in this example, sodium has 1 valence electron. So to take the form of the nearest noble gas, it loses valence electron, now meaning that there is more positive particles than negative particles in its atom. 11 is greater than 10. Do some simple subtraction, it has a +1 charge, because there's 1 more proton than there is electrons. The same thing can be done with calcium. Calcium has 2 valence electrons, and it wants to lose those valence electrons to look like the nearest noble gas, argon. So calcium loses 2, and then protons are greater than electrons. 20 is greater than 18, and subtraction, it has a +2 charge. And then aluminum has 3 valence electrons, and it wants to lose all 3 of them to look like neon. And that means that it has 10 electrons, but 13 protons. Subtraction, it has a +3 charge.
This is a fluorine atom which has 7 valence electrons. It is missing 1, so it gains an electron to give it the shell of the nearest noble gas, neon. Electrons is greater than the number of protons, meaning that it is a negatively charged ion.
The same thing is happening for the oxygen atom. It needs to gain 2 electrons to look like neon, and so it does, meaning that the number of protons and the number of electrons are uneven, giving it a -2 charge.
Opposite charged ions are attracted to each other, so when they come together, they form ionic bonds.
And this is just restating when a positive meets a minus, that is when an ionic bond is formed. And here are some examples. Writing out the core electron configuration can help you identify the valence electrons of an atom. These are the dot diagrams for sodium and fluorine. Sodium loses its electrons, while fluorine is always going to want to gain electrons. So the sodium atom gives off its electron to the fluorine, both ending up with a full outer shell.
And because there's gaining and losing of an electrons, that means that the charge of the atoms is going to be different. So sodium has a +1 charge, while fluorine has a -1 charge because of the imbalances between protons and electrons. So adding those together, +1 and -1 equals 0, balancing out the compound. This is another example of an ionic compound with calcium and oxygen. Calcium has 2 valence electrons while oxygen has 6. And so the calcium doesn't want to, but the oxygen wants to. So they just give them to each other. So the calcium gives its 2 electrons to the oxygen, leading to another neutral compound.
This is another example, except we're using aluminum and oxygen, and they have different wants and needs, so they don't immediately balance each other out, because +3 does not equal -2. So how are we going to do this? Well, I like using this example with blocks to figure out how they go. So you can see that we're missing 1 electron, so we obviously have to add another atom to make sure that they equal each other. And we have to add another oxygen atom to fill out the last 2 electrons. So the aluminum in total gives away 6, but the 3 oxygen atoms want to get 6. And so this is how it balances out at Al2O3.
Of course, you can't always just be naming things after their letters because then things just get long and confusing. So this is how we name binary ionic compounds, which is a metal and a non-metal. So we have sodium and we have fluorine here. But you can't just say sodium fluorine because that's not correct. You always read compounds starting with the metal, and then the non-metal goes at the end. But the ending of the non-metal changes to "ide." So instead of sodium fluorine, it's sodium fluoride.
Now this example is calcium and oxygen, but you can't just read it straight up, calcium and oxygen. No, you have to change the ending on oxygen to oxide. So this compound reads calcium oxide. This last example is with multiple atoms, but it still stays the same. So the metal stays the same as aluminum, but oxygen doesn't stay oxygen, it turns into oxide. So this compound reads aluminum oxide.